What if the universe has already shown us something impossible, and we've been staring right at it all along? Tonight, we journey to the edge of what science can explain, where the laws of physics begin to blur. Welcome to Cosmic Drift. A cloud of rubidium atoms rises inside a vacuum chamber. It is colder than any winter and smaller than a grain of dust. No one watches it with an eye. Lasers do the watching. A pulse of light meets the cloud and divides the quantum wave of each atom into two paths. Another pulse turns the paths. A final pulse brings them together. The atoms fall while this happens. Yet the experiment is not mainly about gravity. It is measuring a kick. One photon enters an atom. The atom recoils. The motion is almost absurdly slight, but the two paths remember it as a difference in phase. When the paths reunite, that difference changes how many atoms arrive at each detector. Count the atoms, know the phase. Know the phase, know the recoil. Know the recoil precisely enough, and a number begins to appear that has no meters in it, no seconds, no kilograms, and no name borrowed from any human measuring system. How can the smallest push from a beam of light reveal the strength of electromagnetism itself? The answer begins with a reversal. A laboratory usually uses known constants to predict what an atom will do. Here the atom is allowed to answer back. The photon carries a known momentum. The rubidium carries a known mass. Their encounter reveals the ratio between the quantum of action and the atom's inertia. Other precision measurements connect that ratio to the energy needed to remove an electron from hydrogen and to the mass of the electron. When those measured relationships are combined, the laboratory extracts the fine structure constant. This is not a value painted on an instrument. It is not assumed before the atoms fly. It is reconstructed from the way matter moves after light touches it. A falling cloud becomes a balance for a photon. The balance is sensitive enough to distinguish changes smaller than 1 part in 100 billion. That is the first reason this number deserves attention. Physics can ask nature for it in radically different languages. One laboratory listens to recoiling atoms. Another traps a single electron and listens to its magnetism. A third reads the spacing between colors in atomic light. The apparatus changes. The measured relationship returns. If a falling cloud of rubidium just changed what a physical constant means to you, subscribe and help me keep turning measurements this precise into investigations we can share. The result is usually written with the Greek letter alpha. Its value is a little more than 7 thousandths. Its inverse is the famous form, a little more than 137. The current recommended inverse value begins 137.035999177. The uncertainty reaches only into the final digits. Saying 1 over 137 is useful shorthand, but it is not exact, and the difference matters whenever a claim depends on numerology rather than physics. Alpha combines the elementary electric charge, the speed of light, the quantum of action, and the electrical property assigned to empty space in the International System of Units. Every unit cancels. That cancellation is not decorative algebra. It removes an escape route. Imagine that a length is reported as 10 meters. Another civilization could describe the same length with another number because it chose another unit, The numerical value is partly about the object and partly about the ruler. The same problem follows a speed, a mass, and many constants that carry units. Change the convention and the digits change while the underlying world does not. Alpha is different. It compares physical effects in a way that survives a change of rulers. Replace meters with feet. Replace seconds with a different interval. Rebuild the entire system of units. Alpha remains alpha. It is a ratio written by nature rather than a label written on nature. This gives us the plausible starting model for the investigation. Perhaps the unexplained constants in physics are merely conversion factors. Perhaps their strange values come from the human habit of measuring one kind of thing with units invented for another. That model works for some confusion. It cannot dissolve a dimensionless number. The next model is more serious. Alpha might simply be a measured property, like the slope of a particular hill. A hill does not need a deeper reason for every angle. Measure it and move on. Physics can do exactly that. Put alpha into the equations, and the equations produce predictions of astonishing accuracy. Nothing prevents a successful theory from containing a measured input. But alpha is not a private detail of one object. It is the low energy strength of the electromagnetic interaction. It enters wherever charged particles and light respond to one another. It helps determine the relative spacing of atomic energy levels, the size of relativistic corrections in atoms, the magnetic behavior of an electron, and the rates of many processes involving light. It is not the only quantity needed to build ordinary matter, and it should not be described as a solitary dial that determines every length and every bond. Mass ratios and the strong interaction matter too. Still, alpha is one of the cleanest dimensionless settings in the whole construction. That leaves a sharper question than why a particular decimal looks strange. What would count as an explanation for the strength of electromagnetism? More digits would not be an explanation. A more precise experiment could add another decimal place and leave the question untouched. A compact formula made from circles and square roots would not be enough either. With enough mathematical ingredients, coincidences can be manufactured around almost any target. A real explanation would have to show why this value follows from a deeper structure, predict something that was not used to build the answer, and survive every scale at which electromagnetism has been tested. That final requirement changes the story. The number near 1/137 is not the same effective strength at every energy. At short distances and high collision energies, the electromagnetic coupling grows. A theory that claims to derive only the familiar low-energy digits has explained a photograph of one point while ignoring the curve that contains it. The goal is therefore not to worship a number. It is to learn what the number is doing, how experiments isolate it, why it changes with the scale of a measurement, and where the current theory finally has to stop and ask nature for an input. The oldest visible clue is light, that almost refuses to split. Heat hydrogen until it glows, and pass the light through a device that separates colors. The result is not a continuous rainbow. It is a set of narrow spectral lines. Each line records a permitted change in the energy of the atom. An electron begins in one allowed state and ends in another. The lost energy leaves as a photon with a matching color. At modest resolution, one of those lines looks single. Improve the instrument, and it divides into components separated by a much smaller interval. This fine structure supplied alpha with its name. The word fine does not mean elegant. It means a detail too narrow for the earlier picture to resolve. The first atomic model could account for the broad pattern by treating the electron as if it occupied a set of quantized orbits. That model was historically powerful and physically incomplete. It left out the electron's spin, the full requirements of relativity, and the quantum field that later replaced the orbit picture. Add the missing effects, and states that once looked equal are no longer exactly equal. Their energies separate. The splitting carries powers of alpha. Why should a number associated with electricity control a gap between colors? Because color is energy, and the atom is an electromagnetic system. The electron is bound to the nucleus by electric attraction. Its motion and spin respond to magnetic effects that appear when the same interaction is viewed relativistically. Alpha measures how large those corrections are compared with the leading atomic structure. In the simplest hydrogen picture, alpha also appears as the ratio between the characteristic electron speed and the speed of light. This does not mean a tiny planet literally circles the nucleus at that speed. The orbit is a teaching carrier, not the final object. Its useful landing is the ratio. Alpha tells us how far ordinary hydrogen sits from the regime where relativistic motion dominates. The same comparison explains why the fine structure is fine. The main atomic energies scale differently from the relativistic corrections. Their ratio is suppressed by powers of a small dimensionless coupling. Alpha is much less than 1, so the correction is narrow enough to hide until the measurement becomes precise. That is a better meaning for 1/137 than a mystical integer. It is a statement about relative strength. Electromagnetic quantum effects can be organized as a series. The first contribution is followed by corrections that bring additional powers of a number near 7/1000ths. Later corrections often become smaller, which is one reason quantum electrodynamics can be calculated with such extraordinary control. The spectral split gives the number a physical face. Two nearly neighboring colors are not separated because a committee chose meters badly. They are separated because the relationship among charge, light, and quantum action has a particular strength. Now the starting model breaks. Alpha is not a conversion nuisance. It is a measurable ratio inside the atom. But breaking that model does not yet explain the value. It only proves that the question is real. There is a second visible face of alpha that does not require resolving two almost identical spectral colors. It can be held as a sheet of carbon-1 atom thick. Graphene is a lattice of carbon atoms arranged in a hexagonal pattern. Remove graphite layer by layer until one atomic plane remains and the material is nearly transparent. Nearly is the important word. A single sheet absorbs about 2.3% of visible white light. That fraction is unexpectedly simple. Under the conditions where graphene's electrons behave like nearly massless quantum particles, the leading absorption is pi multiplied by alpha. Pi times a little more than 7/1000ths gives a little more than 2/100. Expressed as a percentage, the result is about 2.3. The measured opacity is not exact at every wavelength and under every material condition. Interactions, substrate effects, doping, strain, and departures from the ideal electronic structure can add corrections. The original suspended graphene measurements found the simple value within a few percent. The claim is not that every carbon film is a perfect meter for alpha. The claim is that a fundamental electromagnetic coupling emerges directly in the visible response of a material only one atom thick. Why does a constant named after atomic spectral structure govern whether a carbon membrane looks slightly dimmer? Because the same coupling joins light to charged electronic states. Graphene's band structure supplies an unusual density of possible transitions. A visible photon can promote an electron from one state to another. The universal part of the optical conductivity contains the elementary charge and the quantum of action. When the transmission is calculated, their dimensionless combination becomes alpha. The material does not know the history of hydrogen spectroscopy. The photon does not know that a laboratory elsewhere measured rubidium recoil. The repeated value is not a message passing among experiments. It is the consequence of the same electromagnetic rule entering different boundary conditions. Graphene, therefore, pays off the word coupling in an immediate way. Hold a nearly transparent layer in a beam, and a small but visible share of the light disappears into electronic excitations. The absorbed fraction is not alpha by itself, and the exact result carries the geometry factor pi. Still, the scale of the effect is written by the same unitless strength. This anchor also corrects the claim that alpha belongs only to high-energy particle physics. Quantum electrodynamics may sound remote from materials, but graphene's electrons realize a low-energy system whose response exposes the coupling. The bridge runs from a free electron in a vacuum trap to collective electronic states inside carbon. It would be easy to turn this into another overstatement. Alpha does not determine all of graphene's properties. The lattice spacing, electron interactions, defects, temperature, and environment matter. The simple opacity appears because particular dependencies cancel in a particular regime. That cancellation is exactly what makes the result memorable. The spectral doublet and the graphene sheet now perform complementary jobs. The doublet shows alpha through the relative size of a relativistic correction inside an atom. Graphene shows alpha through the probability of light being absorbed by a continuum of electronic states in a two-dimensional material. One requires a spectrometer, the other can affect brightness across visible wavelengths. Neither phenomenon derives the value. Both demonstrate that changing alpha would change an observable ratio. The graphene result also shows why the phrase "one chance in 137" can mislead. The absorbed fraction is about pi times alpha, not alpha, because a measurable probability includes the structure of the process. Other electromagnetic events contain different coefficients, kinematic factors, and powers. The coupling enters the calculation. The experiment decides the final probability. This distinction will matter when virtual particles are added. A leading result may look simple, while higher-order corrections alter it. Precision theory does not discard the simple carrier. It states where the carrier lands and how far it can be trusted. The one atom-thick sheet becomes a memory anchor for that habit. Alpha is not a magic frequency or a hidden color. It is part of the rule that decides how strongly light can create a response in charged matter. The exact response belongs to the system. Suppose alpha were slightly different, while every other independent dimensionless parameter were provisionally held fixed. Atomic energy ratios and relativistic corrections would change. Spectral lines would move by calculable amounts. Electromagnetic reaction rates would shift. For a sufficiently large change, chemistry and stellar processes could become profoundly different. This thought experiment is useful, but it must be kept honest. Nature does not provide a control panel where one parameter can be turned without asking whether a deeper theory links it to the others. Claims about a narrow life-permitting range depend on what else is allowed to change and on which model is used. The safe conclusion is already strong enough. Worlds with different alpha would not merely describe the same physics with different units. They would contain different dimensionless relationships and therefore different observable patterns. The question has moved one step deeper. We began with a kick, delivered by one photon. We found a unitless ratio. We watched it reappear as a split between colors. The next step is to ask what modern quantum theory says the ratio measures. A popular shortcut turns alpha into a fixed chance that light and an electron will interact, about 1 in 137. The shortcut is memorable, and taken literally, it is wrong. Quantum field theory does not assign one universal interaction trial to every passing electron and photon. Probabilities depend on the process, the energy, the geometry, the available states, and the way the experiment is defined. Alpha enters the amplitudes used to calculate electromagnetic processes. After amplitudes are combined and squared, measurable probabilities and rates can contain one or more powers of alpha, along with many other factors. So, alpha is a coupling, not a cosmic coin, with one fixed chance of landing on interaction. The distinction matters because the inaccurate picture would make the later change with energy impossible to understand. A coupling is part of the rule for building predictions. A probability is the result for one specified experiment. This corrected model is less slogan-friendly and more powerful. Wherever an electromagnetic calculation adds another layer of interaction, another factor related to the coupling enters the expansion. The smallness of alpha helps make the later layers manageable. The theory can add effects from virtual particles, vacuum polarization, and complicated loops, then compare the sum with experiments precise enough to notice them. That comparison is where the electron becomes one of the most demanding witnesses in science. Place a single electron inside a penning trap. Electric fields confine it along one direction. A magnetic field bends its motion into a circle. The electron behaves as both a charged particle and a tiny magnet. It circles at one characteristic frequency, while its magnetic orientation responds at another. The small difference between the frequencies contains the electron's magnetic anomaly. The word anomaly can sound like a failure. Here it has a precise meaning. A simple relativistic equation predicts a magnetic factor of 2, quantum fields add a small correction. The electron interacts with the electromagnetic field around it, including the fluctuating possibilities represented by virtual particles. That correction is the anomaly, and quantum electrodynamics predicts it as a series built from alpha. The first correction is comparatively simple. Each higher order requires more possible interaction patterns. By the fifth loop order, the calculation includes thousands of diagrams and contributions from other sectors of the standard model. The result is one of the most elaborate bridges ever built between a parameter and a measurable property. Inside the trap, the experimental challenge is equally severe. The electron must be isolated from stray fields and understood inside a cavity whose own electromagnetic modes can shift the frequencies. The apparatus does not watch a little compass needle turn. It detects quantum jumps. A change in the electron's state alters the minute signal induced in nearby circuitry. After many controlled trials, the frequency ratio yields the magnetic moment. There are two ways to use this bridge. Feed an independently measured alpha into quantum electrodynamics and predict the magnetic anomaly. Then compare the prediction with the trapped electron. That is a severe test of the theory. Or reverse the calculation. Assume the theory is right, measure the anomaly, and infer alpha. These roots must never be confused. An alpha inferred from the electron is extraordinarily precise, but it is not independent of quantum electrodynamics. The recoiling atom gives an independent root. The value of comparing them is exactly that their machinery is so different. The most recent electron magnetic moment measurement improved the experimental precision and, combined with the standard model calculation, implied an inverse alpha close to 137.035999166. The rubidium recoil measurement reported an inverse value close to 137.035999206. The older cesium recoil result landed lower, near 137.035999046. Those strings of digits are difficult to hold in memory, and memory is not their purpose. The visible fact is that the uncertainties are tiny enough for the final digits to become physical arguments. The rubidium and cesium recoil results differ by about 5.5 standard deviations under their stated uncertainties. That is too large to dismiss as ordinary random scatter, yet it does not mean alpha changed between the laboratories. The experiments use different atoms, laser systems, geometries, calibrations, and corrections. An unrecognized systematic effect in one or both measurements is the conservative explanation. New physics is possible only if it produces the exact pattern and survives every other constraint. A discrepancy is a question, not a license. The Committee on Data of the International Science Council handles such tensions through a global adjustment. It combines connected measurements and theory, tracks correlations, and can expand uncertainties when the inputs do not agree as expected. The recommended low-energy inverse alpha for the current adjustment is 137.035999177. A particle data group electroweak review, using a somewhat different and more recent combination, quotes a closely related world average. The last digits depend on which inputs and adjustment rules are included. The mystery does not. This reveals an important difference between knowing a value and explaining it. The laboratories are still negotiating the last measured digits, but every plausible value lies in the same narrow neighborhood. Even perfect agreement would only tell us where alpha is. It would not tell us why the boundary value is there. The electron also prevents a common shortcut. If alpha were merely a feature of hydrogen, perhaps a better model of hydrogen could derive it. The electron's magnetic anomaly is measured without a hydrogen nucleus. The same coupling arrives through a different physical question. It is part of the field theory, not a quirk of one atom. To see that theory without drowning in notation, picture a calculation as a set of possible histories. An electron enters, an electron leaves. Between those boundaries, it may emit and reabsorb a virtual photon. That photon may briefly contribute through a pair of charged particles. More loops add more possibilities. The drawings are not photographs of hidden events. They are bookkeeping devices for terms in a quantum amplitude. At each electromagnetic vertex, the charge coupling enters. When the observable is assembled, powers of alpha organize the correction. Because alpha is small at low energy, the series often becomes less important with each added order, though the number of terms grows and the mathematics remains formidable. This is what it means to call alpha the strength of electromagnetism. It controls how strongly the electromagnetic field couples to charged matter within the calculation. It does not alone specify the outcome. Masses, momenta, spins, geometry, and quantum interference all matter. Alpha sets the scale of the interaction terms that join them. The model ladder now has 3 rungs. Alpha began as a measured ratio that survived every unit change. It became the relative size of fine corrections in atomic spectra. It has now become the coupling that orders quantum electrodynamics. Each rung explains more appearances. None predicts the low energy value. Why not simply calculate the electron's charge from the standard model? Because the standard model is a framework with measured parameters. It tells us how fields transform, how particles interact, and how observables change when the parameters are supplied. The electromagnetic charge is related to the gauge couplings and the mixing of the electroweak fields. Those couplings are inputs. The theory describes their behavior across energy with extraordinary success, but it does not derive their initial measured strengths from a deeper necessity contained inside the model. Calling a quantity a free parameter does not mean it is free to change during an ordinary calculation. Once experiment fixes the parameter under a chosen definition and at a chosen scale, the theory tightly constrains what follows. Free means the theory itself does not select the boundary value. This is similar to being handed the slope of a river at one location and a perfect equation for how the slope changes downstream. The equation may predict every later bend from the starting measurement. It still did not choose the starting slope. The analogy has a limit. A coupling is not literally flowing through space. The change is with the energy or distance scale used to probe an interaction. That change is called running, and it breaks the simplest version of the number 137 mystery. Approach a charged particle from far away, and the surrounding quantum vacuum affects what is measured. Quantum electrodynamics allows virtual pairs of charged particles to contribute around the charge. Their polarization partly screens it at long distances. Probe at a shorter distance, or equivalently, at a higher momentum transfer, and less of that screening lies between the probe and the source. The effective electromagnetic strength grows. The vacuum in this account is not an ordinary material full of tiny permanent dipoles. Virtual particles are elements of the field calculation, not hidden beads waiting to be exposed. The screening picture is a carrier for the sign and scale dependence. Its landing is precise. Radiative corrections make the effective coupling depend on the measurement scale. At very low energy, near the limit of a photon with essentially no energy, the inverse coupling is close to 137.036, near the energy associated with the Z boson. An electroweak analysis gives an inverse electromagnetic coupling close to 127.93 under a standard definition. The inverse became smaller, so the coupling became stronger. This change has been observed directly in electron and positron scattering. It is not a speculative adjustment made to rescue the theory. The pattern of scale dependence is part of the tested architecture. The famous number, therefore, needs a label that popular discussions often omit. It is the low energy value, close to the Thomson limit, under a stated convention. Ask for alpha without a scale and a renormalization definition, and the question is incomplete once high precision is required. That does not make alpha subjective. The definitions are bookkeeping choices, while measurable cross-sections and rates remain independent of the bookkeeping when calculated consistently. Different schemes distribute corrections differently between the coupling and other terms. They must agree on observables. This is another place where unit conventions and physical dependence can be confused. Alpha is dimensionless, so changing meters to feet does not change it. Running is not a change of units. It is a change in the effective interaction revealed by probing at another energy. Nor should running be described as alpha cooling through cosmic history until it came to rest at 1/137. A hot, early universe contained interactions at high energies, so calculations appropriate to those processes use couplings evaluated at high scales. As the universe expanded, the typical energies of many particles fell. That changed which part of the running behavior was relevant to those processes. It did not mean a single universal dial physically slid downward through time and stopped. The correction matters because it transforms the governing question. Why is alpha 1/137 is too narrow? Which alpha, measured at what scale, under what definition? A deeper theory would need to produce the boundary condition and the running behavior together. The standard model already predicts much of the curve once the low energy input and particle content are known. The unresolved part is why the theory begins with those gauge couplings and that particle content. Running also defeats a large family of numerical tricks. Suppose a compact arrangement of pi, whole numbers, and square roots matches the low energy inverse value through several digits. Even if the match is exact, what does it predict at the energy of the Z boson? What happens when a new charged particle threshold enters the vacuum polarization? Which renormalization definition does the formula describe? Unless it produces the scale-dependent observables and something genuinely new, it is a fit to a target, not an explanation. This standard may sound severe. It is the same standard that makes the electron magnetic moment meaningful. Quantum electrodynamics does not merely reproduce one-digit string. It connects alpha to an independent observable through thousands of terms. Atom recoil then checks the input without relying on that same magnetic calculation. Agreement across independent machinery is what turns algebra into physics. The remaining recoil discrepancy is therefore useful even if it ends with a loose cable, a subtle wavefront, or an underestimated correction. Precision is not a ceremonial display of decimals. It is a way to make theories and apparatus expose their hidden assumptions. The experiment with rubidium contains a vivid example. A laser beam is never a perfectly flat plane. Its wavefront curves. Atoms at different positions can receive slightly different effective kicks. The cloud has a finite temperature and expands. Gravity changes trajectories. Magnetic fields shift states. Each effect must be measured, modeled, reversed where possible, and assigned an uncertainty. The final number is not the output of one clean push. It is the surviving result after a campaign against every known imitation of that push. The electron trap faces a different campaign. The cavity changes the electron's motion. The magnetic field drifts. Detection can heat the system. The theory must include contributions from heavier particles and from hadrons, even though the electron itself appears elementary. When the routes converge, their independence is the source of confidence. When they separate, their independence helps localize the problem. This is the opposite of an occult number appearing everywhere by magic. Alpha reappears because well-defined electromagnetic observables depend on the same coupling. The wonder is not that the symbol turns up. The wonder is that one framework carries the value across such different experiments and still predicts their relationships beyond a part in a trillion. Now the boundary of knowledge can be stated cleanly. Direct knowledge tells us the outcomes of recoil, spectral, scattering, and magnetic measurements. Quantum electrodynamics links those outcomes through a coupling and predicts its running. The standard model places that coupling inside a broader electroweak structure, but the model does not derive the measured low-energy boundary value from a more fundamental principle. That boundary is not a failure of the calculations. It is the place where calculation begins. The next question is whether the same boundary value has remained stable across places and ages. That sounds like another version of running. It is not. Separating those two ideas is the key to reading a natural reactor, an atomic clock, and light that crossed half the observable universe. Running asks how the effective coupling depends on the energy scale of an interaction here and now. Variation asks whether the underlying low-energy parameter itself differs with location or cosmic time. The first is established quantum field behavior. The second would require new physics and has not been confirmed. The distinction can be tested because atoms preserve ratios. If alpha changes, different electronic transitions do not all move together. Some energy levels are more sensitive to relativistic electromagnetic effects than others. Compare the right transitions, and a drifting alpha would appear as one clock slowly changing its beat against another. Modern optical clocks are built from atoms or ions, whose quantum transitions are so narrow that time can be divided with extraordinary stability. One clock might use strontium, another might use a charged ytterbium atom. A cesium fountain provides another reference. Their frequencies depend on alpha and on other dimensionless quantities in different combinations. A simple comparison cannot automatically blame alpha for any drift. The electron to proton mass ratio and nuclear magnetic properties can also enter. Researchers build a network of sensitivities and solve for the combinations the data can constrain. Over intervals from minutes to years, the clocks have found no confirmed temporal change in alpha. They convert silence into limits. Silence is not proof of eternal constancy. It tells us that any allowed drift must be smaller than the experiment's reach, or shaped in a way the chosen comparison cannot see. Some models predict smooth change. Others predict oscillations from a light field that could make constants vary at a particular frequency. The data must be searched for, both without assuming that one absence excludes every possibility. The geological test reaches much farther back. In Gabon, uranium ore preserves evidence that parts of a deposit sustained natural fission reactions roughly 2 billion years ago. The ingredient was not lost technology. The isotope balance of young Earth was different. Uranium with the mass number 235 was more abundant than it is today. Water moving through rich ore slowed neutrons and helped the chain reaction continue. Heat removed the water, the reaction weakened, and later water could return. The rock became a reactor without a builder. Fission products left an archive. Among them, samarium is especially useful because one isotope captures neutrons through a resonance at an unusually low energy. The position of that resonance depends on a near cancellation between nuclear and electromagnetic contributions. Change alpha and the electromagnetic part shifts because the final resonance energy is much smaller than the large terms that combine to make it. A small change can leave a magnified effect in the surviving isotope ratios. This makes the natural reactor a sensitive probe, but not a simple fossil meter. Researchers must reconstruct the neutron spectrum, operating temperature, water content, and nuclear response. The relationship between a resonance shift and a change in alpha relies on nuclear modeling. Later analyses have revisited those uncertainties and still obtain strong bounds, but the exact number is not carved directly into the rock. A careful modern summary is that Oklo is consistent with no change and constrains the relative difference in alpha over that span to roughly parts in 100 million, with model-dependent details. Some later analyses argue for a limit around 10 parts per billion. The range should be presented as a bound with nuclear assumptions, not as a perfect measurement of the ancient constant. The value of Oklo is conceptual. A reactor that operated before complex animals existed can test a dimensionless coupling today because nuclear resonances preserve a comparison. The rock does not remember meters or seconds. It remembers which neutrons nuclei were willing to absorb. Now extend the baseline from a continent to intergalactic space. A quasar is bright enough to illuminate gas that lies between it and Earth. atoms and ions in that intervening cloud absorb particular wavelengths, leaving dark lines in the quasar spectrum. The light then continues for billions of years before entering a telescope. Those absorption lines record atomic energy differences when the universe was much younger. If alpha had a different value in that cloud, transitions with different sensitivities would shift by different relative amounts. The whole spectrum is already stretched by cosmic expansion, but a common redshift moves all lines together. Variation in alpha changes the pattern among them. The measurement is therefore another comparison of comparisons. The difficulty is that the required shifts are tiny. A spectrograph's wavelength scale can distort across its detector. The absorbing gas may contain several clouds moving at slightly different velocities. Isotopic abundances may differ from those on Earth. Lines overlap. A model can fit the same profile in more than one plausible way. Any one of these effects can imitate or conceal the signal. Earlier large samples produced claims of a possible spatial pattern in alpha. Those claims made the question urgent, but calibration distortions and model choices complicated the interpretation. A result becomes more trustworthy when the instrument is designed to control the known failure modes, and the analysis is blinded before the answer is revealed. The European Southern Observatory's espresso spectrograph supplies such a test. It observed a bright quasar whose light passes through a strong absorption system at a redshift a little above 1. A laser frequency comb provided a dense grid of reference wavelengths. High spectral resolution revealed narrow components that older instruments could blend together. The researchers initially hid the inferred alpha offset while they chose models and estimated systematics. Their result was a relative difference of about 1.3 parts per million, with a statistical uncertainty of about the same size and a smaller systematic uncertainty. In other words, it was consistent with no variation. Combining it with other carefully calibrated measurements also produced a result consistent with 0 at the level of roughly parts per million. This does not erase every earlier claim by decree. Different data sets, directions, absorbers, instruments, and modeling assumptions must be compared. It does establish that one of the cleanest modern sightlines does not require alpha to have changed. The quasar test also exposes an important limit in language. Saying that a spectrum shows the value of alpha 8 billion years ago is useful compression. The instrument actually measures relative wavelengths. Atomic calculations tell us how those wavelengths respond to alpha and other effects. A model of the absorbing gas separates velocity components. The final alpha constraint is an inference built from direct spectral evidence, not a digit printed on an ancient photon. That chain does not weaken the science, it locates the science. Each link can be tested, improved, or challenged. The three archives now cover very different baselines. Atomic clocks compare the present across years. Oklo reaches into geological time through nuclear products. Quasar absorption reaches across billions of light years and much of cosmic history. None has confirmed a change in the low-energy fine structure constant. This creates a paradox. Only if running and variation were blended at the start. The coupling can be stronger when measured at high interaction energy while remaining the same low-energy boundary parameter across time. Energy dependence is not historical drift. Imagine two photographs of a coastline. One is taken from far above and one from a few meters away. Their measured lengths differ because finer resolution reveals more detail. That is a rough carrier for scale dependence. Now imagine returning a century later with the same resolution to ask whether erosion changed the coast. That is variation with time. Resolution and history are different questions. The coastline analogy eventually breaks because renormalized couplings are not geometric lengths, but its landing is useful. Always hold the probe scale fixed before asking whether the constant changed with place or time. Why search for variation if the standard model treats alpha as constant? Because a deeper theory might turn the measured parameter into the value of a field. If that field evolves, couples to matter, or responds to dark matter, alpha could vary or oscillate. A detected change would not merely revise one table of constants. It would reveal a new degree of freedom and challenge the local position invariance built into our current description of nature. The absence of a detected change cuts away possibilities. Any proposed field must couple weakly enough, evolve slowly enough, or hide in frequencies and environments not yet excluded. Precision clocks and astronomical spectra become particle detectors without colliding particles in the usual way. This is one of the larger consequences of an unexplained parameter. Because alpha is measured so precisely and appears in many systems, it can expose inconsistencies that point beyond the theory. The lack of an explanation does not leave physics helpless. It turns the parameter into a sensor. The same logic governs the recoil disagreement. A mismatch between rubidium, cesium, and the electron magnetic moment could come from apparatus, calculation, or new physics. Each possible cause has a different signature. Repeat the measurements with new atoms, change the geometry, improve the quantum electrodynamics calculation. Search for a hypothetical particle through other effects. A vague anomaly becomes useful only when alternatives are forced to make separate predictions. This gives us a standard for the phrase unexplained number. It should not mean scientists have stared at the digits and failed to think of a story. It means the accepted theory takes a measured boundary condition as input, while candidate deeper theories have not earned confirmation by predicting that input and additional evidence. The distinction protects the investigation from two opposite exaggerations. The first exaggeration says physics knows nothing about alpha. In fact, physics knows how to measure it through independent routes, how it shapes atomic corrections, how it enters quantum electrodynamics, how it runs with energy, and how stable it appears across enormous spans of space and time. The second exaggeration says a precise measurement is almost an explanation. It is not. A map can locate every stone in a wall without explaining why the architect chose that wall. What would an explanation look like in practice? It might show that the electromagnetic coupling is not independent. Perhaps several forces emerge from one interaction at high energy, and the low energy values follow from how that unified interaction separates and runs. Perhaps charge is fixed by a deeper symmetry, geometry, or consistency condition, Perhaps a dynamical field evolves toward a value through a mechanism that also predicts measurable departures elsewhere. Perhaps an ensemble of possible values and a selection effect explains why observers encounter a narrow region, though that route would need a justified distribution and independent consequences. These are categories, not answers. Each one owes more than a phrase. Unification must specify the symmetry, particle content, thresholds, and symmetry breaking. It must run the couplings down to measured energies and match precision data. A geometric derivation must connect the mathematics to actual fields and predict the scale dependence. A dynamical mechanism must explain stability and survive clock, Oklo, Quasar, and equivalence principle constraints. A selection argument must show what varies, how possibilities are weighted, and why the observed value is typical enough to expect. The standard is demanding because the present theory is already accurate. A replacement cannot merely sound deeper. It must reproduce everything that quantum electrodynamics gets right, then explain the input or predict a deviation. This is why the number is more useful than a general statement that the universe is mysterious. Alpha marks a specific debt. The theory writes it in a definite place. Experiments measure it by named procedures. Candidate explanations can be asked for receipts. Before those candidates can be judged, one more conceptual trap must be removed. Does the value 1 over 137 determine whether matter exists at all? The answer is not in that simple form. Electromagnetism is essential to atoms and chemistry, but alpha is part of a system. The electron mass relative to nuclear masses affects atomic scales. The strong interaction helps set nuclear masses and stability. Quark masses influence which nuclei exist. Gravity shapes stars that manufacture elements. Changing alpha while freezing every other parameter is a defined thought experiment, not a guaranteed menu of physically possible universes. Within that thought experiment, stronger electromagnetism increases relativistic effects and alters nuclear electric repulsion. Atomic and nuclear structures change. Weaker electromagnetism reduces binding and reaction rates in other ways. Large changes can remove familiar chemistry, but a dramatic claim such as 1 tiny percentage would destroy all life requires a specified model and calculation. Without them, it is packaging disguised as precision. The honest version is more durable. Alpha lies in a region compatible with the complex atoms and chemistry we observe. We do not yet know whether a deeper theory permits many other values, correlates alpha with other parameters, or uniquely selects this one. That answer may feel less theatrical. It is also the point where genuine discovery can begin. The governing question has now acquired an answer boundary. We can explain what alpha measures, how it affects observables, why it depends on energy scale, and how experiments test its constancy. We cannot currently derive its low energy boundary value from an experimentally confirmed deeper theory. Everything that follows asks which proposed route could cross that boundary without pretending it has already done so. The most established route begins with electroweak theory. At everyday energies, electromagnetism and the weak interaction look utterly different. The photon is massless and reaches across long distances. The carriers of the weak force are massive, so the interaction acts over a tiny range. Yet the standard model describes both as parts of one gauge structure. The familiar electric charge emerges from two gauge couplings and a mixing angle after the electroweak symmetry is broken. That is already a deep unification of behavior. It explains relationships among photons, W bosons, Z bosons, and charged particles. It does not fix the two-gauge couplings themselves. Their measured values still enter as parameters. Run the electromagnetic, weak, and strong couplings toward higher energies, and their strengths change at different rates. The lines move closer. This suggests that at a sufficiently high scale, they might become manifestations of one unified coupling. The suggestion is not the same as a meeting. Using only the confirmed particle content of the minimal standard model, the couplings do not converge at one exact point in the simplest way. Add new particles, new thresholds, or supersymmetric partners, and the running can change. Some grand unified theories produce more attractive convergence. They also tend to predict new effects, such as proton decay, magnetic monopoles, or relationships among charges. Experiments have not confirmed the simplest expected signatures. The proton decay searches have pushed lifetimes far beyond early expectations. Collider searches have not found the simplest supersymmetric particle spectrum. More elaborate models remain possible because threshold corrections and high-scale physics can reshape the result. That flexibility is both a resource and a danger. A framework that can be adjusted after every null result has not yet explained alpha. Suppose a future unified theory contains one coupling at high energy and a fixed set of particles. The theory would predict how that coupling runs through every threshold. It could then produce the low energy alpha along with the strong and weak couplings. If the same structure predicted particle masses, decay rates, or a new symmetry that experiments later found, the explanation would have leverage beyond the original target. Even then, a question remains. What fixes the unified coupling? Unification can reduce several inputs to one without reducing one to zero. That is progress. It is not necessarily the final layer. Explanation in physics often means compression rather than absolute removal. Newton compressed many falling motions into one law while leaving other parameters to be measured. A theory that turns three unrelated couplings into one measured coupling has explained a relationship even if it has not explained existence itself. The right demand is therefore not that every answer end all possible questions. It is that an answer reduce independent assumptions and make new successful predictions. Another route looks to charge quantization. Every observed free particle carries electric charge in exact-looking units. The electron and proton have opposite charges, equal in magnitude to extraordinary precision, even though the proton is composite. Quarks carry fractional charges that combine into whole charges for ordinary hadrons. The standard model arranges these assignments through gauge symmetry and consistency, conditions that cancel quantum anomalies. Grand unified groups can place different particles into common multiplets, making the pattern of charges feel less accidental. This may explain why charges come in the units they do. it still does not automatically determine the strength of the common coupling. The unit of charge and the value of the coupling are related ideas but not identical debts. That distinction prevents another false derivation. Showing why the electron has one unit of charge does not by itself show why the electromagnetic interaction has its measured dimensionless strength. A rule can quantize the allowed labels while leaving the scale of the interaction free. Geometry offers a more ambitious possibility. In theories with extra spatial dimensions, the fields seen in ordinary spacetime may descend from geometry or fields living in a larger space. Couplings can depend on the size and shape of hidden dimensions. A measured constant could then be a shadow of a compact geometry. This sounds like the desired derivation, but it moves the question unless the geometry is selected. Why that shape? Why that size? What stabilizes it against change? How many possible compactifications exist? Can the proposal reproduce the observed particles and avoid unobserved forces? A candidate becomes explanatory when the same geometry produces a network of results. If it yields alpha only after the geometry is chosen to match alpha, the circle has merely grown larger. The dynamical route takes the possibility of variation seriously. Perhaps alpha reflects the value of a scalar field. The field could evolve toward a minimum of a potential, and its position would set the electromagnetic coupling. Then the number would be an outcome of cosmic dynamics rather than an arbitrary input. But a field that talks to electromagnetism usually talks to matter. If it is light enough to evolve today, it may produce a new long-range force or violate the equivalence principle. It may make alpha drift in clocks, oscillate with dark matter, or differ across gravitational environments. The null results already discussed restrict those couplings sharply. This is a productive kind of difficulty. The proposed explanation generates tests. A clock network can search for a shared oscillation. A satellite experiment can compare freefall for materials with different electromagnetic binding energy. Spectra can test distant epochs. A model that survives becomes more than a story about a number. Selection arguments begin from a different direction. If a deeper framework permits many regions or universes with different effective constants, observers will only arise where stable structures are possible. Finding alpha in a compatible region would then be unsurprising. The logic can be valid and still incomplete. To make a prediction, one needs to know which parameters vary, the distribution of possibilities, correlations among constants, and the conditions required for observers or complex structures. Change the weighting, and the expected value can change. If the argument only says we observe a value compatible with our existence because otherwise we would not observe it, it has explained the observation too weakly to select the digits. Selection can contribute to an explanation without deriving an exact number. It may account for why a parameter lies inside a broad, viable window, while a dynamical theory determines the distribution. The result would be a layered explanation rather than one magic equation. Pure mathematical formulas occupy a separate category. A dimensionless constant naturally invites comparison with dimensionless mathematical quantities. Pi, exponential functions, prime numbers, and group dimensions can be combined into compact expressions that approach the measured value. Coincidence is easy to underestimate. The number of short expressions grows rapidly as operations and constants are added. Search long enough after knowing the target, and a close match becomes likely. The match gains evidential force only if the structure was independently motivated and predicts more than the target. Running supplies a decisive test. The low energy number is 1 point on a scale-dependent relationship, a formula that returns 137.035999 without specifying energy and definition has not described the full object. If it cannot predict how charged particle thresholds change the effective coupling, it is not a replacement for quantum field theory. This does not mean mathematics cannot determine alpha. Modern physics is built from mathematical structures. It means numerical resemblance alone cannot show which structure nature uses. There is a useful comparison with the proton mass. Most of the proton's mass is not simply the sum of the small bare masses assigned to its quarks. It emerges from quantum chromodynamics, the energy of confined fields, and the scale generated by the running strong coupling. Once the high-energy inputs are supplied, powerful calculations can predict hadron masses. The proton demonstrates that a number can become understandable through a mechanism rather than a closed-form expression. The explanation is a theory that generates the scale and connects many observables. A future account of alpha may look similar. It may not print the inverse value from a line of elementary constants. It may show how a deeper field content, symmetry, and boundary condition produce the entire pattern. What would convince us? First, the theory would identify the relevant coupling under a precise definition. Second, it would predict the low energy value with uncertainties small enough to compare with recoil and electron measurements. Third, it would reproduce the observed running through known particle thresholds. Fourth, it would connect alpha to at least one independent result not fitted in advance. Fifth, it would survive searches for new particles, varying constants, equivalence principle violations, and rare decays. This list is not bureaucracy. It is how an explanation stops being a coincidence. It also shows why the last digits matter. If two independent atom recoil measurements disagree beyond their uncertainty budgets, a candidate theory cannot choose whichever value looks prettier. The experimental tension must be resolved or incorporated through a specific effect. Precision prevents an explanation from hiding in rounding. The phrase 1/137 can now be repaid honestly. It is a memorable approximation to the inverse low-energy coupling. It is not an exact integer, not a universal probability, not the same value at every energy, and not known to arise from mystical arithmetic. Its importance comes from the web of measurable relationships it organizes. Return to hydrogen. The narrow split between spectral lines is one node in that web. Return to the falling rubidium cloud. The recoil phase is another. Return to the trapped electron. Its magnetic anomaly is another. Return to high-energy scattering. The running coupling is another. Return to Oklo and the Quasar. Their silence constrains any field that would make the boundary drift. The conceptual anchors now carry different jobs. The spectral doublet makes the coupling visible. The atom interferometer shows how it is measured independently. The electron trap tests the quantum calculation. The changing strength with energy prevents a static numerical answer. The geological and astronomical archives test whether scale dependence has been confused with change across history. If any proposed explanation cannot travel through all of those anchors, it has explained only a fragment. There is another question hiding beneath the demand for derivation. Why should nature be explainable by fewer inputs at all? Physics has often succeeded by discovering that quantities thought independent were connected. Electricity and magnetism became one field. Space and time became one geometry. The electromagnetic and weak interactions became parts of one gauge theory. Those successes encourage the search for a deeper source of alpha. They do not guarantee that the search ends in a unique number. A final theory might contain environmental parameters, historical initial conditions, or several consistent vacua. The expectation of complete derivability is a scientific hope informed by past compression, not an established law. This is where intellectual honesty becomes part of the result. Saying we do not know why alpha has its boundary value is not the same as saying no reason exists. Saying a theory has free parameters is not the same as saying the parameters are random. Saying many candidate ideas remain is not evidence that all are equally good. Evidence ranks them. A model with a mechanism and risky predictions stands above a numerical fit. A framework that reproduces several independent relationships stands above one that reproduces one decimal. A null result can lower confidence without proving every variant impossible. The map has gradients even when the destination is unknown. The fine structure constant is valuable because it forces those distinctions into a small space. It is measured, not guessed. It is stable within severe tests, not assumed without challenge. It runs with energy in a predicted way, not with time in any confirmed way. It is accepted as an input, not derived inside the standard model. Every clause has a different evidence status. That precision in language is not a restraint on wonder. It is what allows the wonder to survive contact with measurement. The atom recoil route deserves one slower pass because it shows exactly how a constant can be measured without being seen. Begin with the kick. A photon carries momentum set by its wavelength and the quantum of action. When an atom absorbs the photon, momentum conservation requires the atom to move. If the atom later emits a photon in a controlled direction, it receives another kick. Repeated interactions can transfer many photon momenta and magnify the effect. The rubidium experiment does not follow a tiny ball along one sharp path. A sequence of laser pulses prepares superposed momentum states. The atomic wave packets separate, evolve, and recombine. Their phases depend on the recoil frequency, which compares the energy of the kick with the quantum rate at which phase accumulates. Interference converts that phase into populations. At one output, more atoms are counted. At another, fewer. Change the laser frequency, and the pattern moves. Reverse the direction of momentum transfer, and some systematic shifts reverse too. Repeat the sequence with carefully chosen timings, and the recoil contribution can be isolated from gravity, vibration, and laser noise. The immediate result is a ratio involving the quantum of action and the mass of rubidium. That is not yet alpha. The experiment then enters a chain of independent knowledge. Atomic mass spectrometry connects the rubidium atom to the unified atomic mass scale. Precision spectroscopy supplies the Rydberg constant, which describes the leading energy scale of hydrogen. Other relations connect that scale to the electron mass and alpha. When the chain is solved, alpha emerges. Every link contributes an uncertainty and a correlation. The final precision is possible because some links are already known even better than the recoil ratio. This chain is an important answer to the question of whether the experiment secretly assumes the number it claims to measure. The theoretical relationship contains alpha, but the measured inputs do not all come from the same electromagnetic observable. The method is designed so the unknown coupling can be isolated. Its independence from the electron magnetic anomaly is why comparing the two routes tests quantum electrodynamics. The phrase independent does not mean theory-free. No precision extraction is theory-free. Momentum conservation, quantum phase evolution, atomic structure, and mass relationships all enter. Independence means the dominant experimental information and the critical theoretical dependence differ from those in the other route. A shared, hidden assumption must be identified rather than merely suspected. The cesium experiment uses the same broad idea and different implementation choices. Its atom optics can transfer large momentum through sequences of light pulses. Its systematic budget depends on cloud properties, beam alignment, wavefront shape, and the way trajectories sample the light. Rubidium has its own apparatus and corrections. Their disagreement is scientifically uncomfortable precisely because both methods are sophisticated enough to make simple dismissal impossible. A new recoil experiment can do more than choose a winner. It can change atomic species, reverse trajectories, reshape beams, and vary cloud temperature to make suspected systematics scale in recognizable ways. If the inferred alpha changes with a controllable laboratory parameter, the apparatus has revealed the imitation. If it remains fixed across new designs and still conflicts with another route, the theoretical stakes rise. Now follow the electron route with the same discipline. The magnetic anomaly is a dimensionless difference between two frequencies. The trap measures it with one electron. Quantum electrodynamics predicts it as a long series whose leading term depends on alpha and whose later terms include heavier leptons, hadronic vacuum polarization, and weak effects. Reverse the prediction, and the measured anomaly becomes an alpha determination. The spectacular precision of that inferred value depends on two achievements. The electron frequency measurement must be stable, and the theoretical coefficients must be calculated. A numerical error in a high-order term or an omitted physical contribution would shift the inference. Independent recoil protects against both possibilities. This is why an apparent agreement cannot be summarized as the experiment confirms the theory to 12 decimal places without qualification. The comparison has several uncertainty sources, and some alpha values are inferred using the theory being tested. The clean test uses an independently measured alpha, carries its uncertainty through the calculation, and then compares the predicted anomaly with the trapped electron. The logic resembles a triangle. One side is atom recoil. One side is quantum electrodynamics. One side is electron magnetism. Measure two and predict the third. A discrepancy tells us the triangle does not close, but it does not label the faulty side. This triangle is a stronger narrative than the claim that a mysterious number appears everywhere. Nothing is merely appearing. Experiments and theory are cross-examining one another through shared relationships. The same courtroom extends to spectral lines. Hydrogen fine structure depends on alpha, but extracting alpha from a line also requires masses, nuclear properties, and higher-order corrections. Some atoms are more useful than others because particular transitions amplify sensitivity or reduce nuclear uncertainty. Precision physics is the craft of choosing observables whose unwanted dependencies cancel or can be measured elsewhere. That craft also explains why dimensionless constants are privileged in discussions of variation. Suppose someone claims that the speed of light changed in the past. A speed carries a unit of distance divided by time. If the length standard and clock behavior also change, the statement can become ambiguous. What any experiment finally measures is a ratio between physical processes. A dimensionless combination reveals what changed relative to what. Alpha already is such a combination. A claim that alpha varied cannot be removed by redefining the meter or second. That does not tell us which dimensional ingredient in a chosen formula should be said to vary. The elementary charge, the quantum of action, and the vacuum electrical constant are connected by unit conventions and definitions. The invariant experimental content is the change in their dimensionless combination. This prevents a misleading question. If alpha changed, was it really the charge changing or the speed of light changing? Without a deeper model that gives those quantities separate dynamical meaning, the division can be conventional. The physical statement is that electromagnetic observables changed relative to other dimensionless standards. A scalar field model can make the statement more specific. It may couple to the electromagnetic field in a way that changes the effective dimensionless interaction. Then the theory predicts how atomic transitions, masses, and free fall respond together. The model supplies the additional structure needed to interpret the variation. The distinction between a measured ratio and its ingredients also clarifies why alpha does not single-handedly set the size of an atom. In a chosen unit system, the Bohr radius can be written using alpha, the electron mass, and the quantum of action. Change only alpha within a defined model, and the radius changes. But the dimensionless size of the atom must be compared with another physical length, and that comparison may involve other parameters. Ordinary matter is a network, not a puppet controlled by one string. The title promise survives without exaggeration. Alpha is important not because it is the only number that shapes reality, but because it is one of the cleanest places where the electromagnetic part of that network becomes a pure ratio. Running adds another layer to the measurement chain. The low energy value can be defined through the response to an electromagnetic probe with vanishing momentum transfer. At higher momentum transfer, charged particle loops modify the photon propagator. Electrons contribute first. As the energy crosses scales associated with heavier charged particles, muons, tau particles, quarks, and hadronic effects enter. The effective coupling, therefore, changes in a structured way. It does not jump arbitrarily whenever a new particle becomes possible. Quantum field theory supplies equations that connect the scales and matching rules that account for thresholds. The particle content controls the slope. This is why high-energy running contains information about unseen matter. A new charged particle would contribute above its characteristic scale and could subtly alter the curve. Precision scattering and electroweak fits can search for that deviation even if the particle is not produced as a clear resonance. The hadronic contribution makes the calculation harder. Quarks at low energies are confined, so simple perturbation theory cannot describe every effect reliably. Researchers use data from electron and positron annihilation and results from lattice quantum chromodynamics to estimate how hadrons polarize the vacuum. The uncertainty in that contribution matters for high-precision electroweak predictions. Here again, the theory is neither helpless nor complete. It predicts the form of the running and incorporates measured hadronic information where calculation is difficult. It still requires the low-energy electromagnetic boundary and the masses and charges of the particles that contribute. If a grand unified model proposes new fields, their effect on running is not optional decoration. Add a charged field and the curve changes. The model must pass through the measured low-energy value, the electroweak scale, and every precision constraint between them. A neat convergence plot drawn without realistic thresholds can suggest a direction. It cannot certify unification. This is the burden carried by the word derive. To derive alpha is not to manipulate its current value until a familiar constant appears. It is to produce the relevant observable relationship from inputs that were not chosen to match it. Consider a theory that predicts one high-energy gauge coupling and a complete particle spectrum. Renormalization equations carry that coupling downward. Symmetry breaking mixes fields. Heavy particles drop out at their thresholds. At the end, the theory predicts the low-energy alpha. If the prediction matches, and the new particles or rare processes are found, the explanation has earned force. Now consider a formula discovered by searching combinations of mathematical constants until one matches the low-energy inverse alpha. The formula has no particles, no thresholds, no scale, and no additional observable. The number may be beautiful. The evidential chain is empty. Both can be printed on one line. Only one can explain. The question of why alpha has this value therefore belongs to experimental design as much as metaphysics. The answer will be recognized through a pattern of successful risks. A theory will predict where another measurement should land, which new state should exist, or how a coupling should change before the data are folded into it. The current standard model already demonstrates that style of success. It used electroweak structure to predict relationships later tested with W and Z bosons. Quantum electrodynamics predicted small corrections that the electron trap could resolve. Those victories justify asking whether the remaining input can be compressed again. They also warn against moving the goalposts. If a proposed explanation needs one parameter to fit alpha, another to hide variation, a third to evade particle searches, and a fourth to repair running. It may contain more independent assumptions than the constant it set out to explain. Explanation is an accounting exercise. Count what was assumed. Count what was predicted. Count which predictions could have failed. Under that accounting, the fine structure constant is still unpaid. The balance is not zero merely because the theory using it is spectacularly successful. Success after an input and explanation of the input are different achievements. The International System of Units provides a final demonstration. For much of modern metrology, certain electrical constants were assigned exact conventional values. Then the system was rebuilt around fixed values for the speed of light, the elementary charge, the Planck constant, and other defining constants. The units became anchored to invariant physical relationships rather than stored objects. Fixing the elementary charge and the quantum of action did not fix alpha. Instead, the measured uncertainty moved into quantities such as the electric and magnetic properties assigned to vacuum in that unit system. Human definitions can decide how amperes and volts are realized. They cannot vote the dimensionless electromagnetic coupling into a preferred value. That is a subtle victory for the original question. We tried to escape through units and found that modern metrology has already performed the experiment. Hold the chosen conversion constants exact, and alpha remains an empirical input. The ruler can be redesigned. The ratio still has to be asked of nature. The atom interferometer asks through motion. The electron trap asks through magnetism. Neither instrument sees alpha directly, because constants are not objects. Each creates an observable whose dependence on alpha is established by a network of theory and other measurements. This is how deep quantities are usually known. Gravity is inferred from trajectories. Fields are inferred from forces and phases. A coupling is inferred from how interaction rates and energy levels fit together. The absence of a direct photograph is not an absence of evidence. Could a future measurement discover that the accepted value is wrong? It could revise the final digits. The recoil disagreement makes that possibility immediate. A corrected systematic or new measurement may shift the recommended adjustment. But any revision compatible with the current evidence will remain extremely close to the familiar low-energy value. The large conceptual question is insensitive to which laboratory wins the last decimal argument. Could a new particle explain the disagreement? Only with work. A new particle that changes the electron magnetic moment might alter the alpha inferred through quantum electrodynamics, while leaving atom recoil different. Yet the particle would also affect other observables according to its mass and couplings. The same idea must face collider searches, precision spectroscopy, scattering, and astrophysical limits. Calling the mismatch new physics before that network is satisfied would reverse the order of evidence. Could alpha itself be an illusion created by renormalization conventions? No, the numerical value assigned to a running coupling depends on a definition, but measurable relationships among cross-sections, frequencies, and recoil phases do not. A convention can move terms between the coupling and the corrections. It cannot remove the empirical content. When two teams use the same consistent definition, they can compare results, Could the value be necessary because any other value would make mathematics inconsistent? No established theorem shows that for the low-energy electromagnetic coupling, quantum field theories can be written with a range of coupling values, at least as effective descriptions. Consistency places constraints on charges, anomalies, and high-energy behavior, but it has not selected the observed boundary value by itself. Could it be an accident? Accident is not a mechanism. It may mean the value is contingent on a vacuum state or historical condition rather than forced by logic. That is possible. A scientific account of contingency would still describe the space of alternatives, the process that selected one, and the evidence expected from that process. The governing question can now be answered without pretending to close it. What would count as explaining alpha is a theory that reduces the measured low-energy coupling to deeper, independently supported structure and predicts the scale-dependent observables that carry it. The standard model does the second half after receiving the boundary value. It does not yet do the first. This answer changes the meaning of the mystery. The mystery is not that physicists cannot interpret 137. They can interpret the coupling in exquisite detail. The mystery is that the interpretation bottoms out in a parameter supplied by experiment. That bottom is visible in the formal structure. Write the standard model, and several numbers must be inserted. Particle masses, mixing angles, and gauge couplings are among them. The theory then creates an enormous field of predictions. Alpha is one clean doorway into the larger parameter problem. Explaining it alone may be impossible because the parameters could be linked. A theory that fixes the electromagnetic coupling may also need to explain the weak mixing, the strong coupling, particle representations, and thresholds. Pull on alpha and the rest of the standard model may move. This is why the most successful future answer may not mention 137 at the start. It may begin with a symmetry or quantum consistency condition that seems unrelated. It may predict a new particle. That particle may change the running above a threshold. The full calculation may descend through broken symmetries until the low-energy coupling emerges. Only at the end would the familiar inverse value appear as one check among many. The number would then lose some of its isolation and gain an explanation. Until that happens, precision work continues on both sides of the bridge. Experimental teams refine atom recoil, electron magnetism, clocks, and spectra. Theorists improve high-order calculations and build models that connect couplings. Neither side can substitute for the other. A beautiful theory, without an independent prediction, is unfinished. A perfect measurement, without a deeper relation, remains an input. The atom cloud at the beginning can now be seen differently. It was not merely measuring a constant. It was testing whether several branches of physics agree on the same boundary condition. Atomic mass measurements, optical frequencies, quantum recoil, and relativity all had to meet. The result could then be carried into a calculation of the electron's magnetism and compared with an entirely different apparatus. One small kick became a consistency test for the standard model. That is the consequence hidden by the phrase unexplained number. Alpha is not valuable only because its origin is unknown. It is valuable because its precision lets it interrogate everything around it. A mismatch can reveal a flawed wavefront, a missing correction, or a new interaction. The constant is both an input and an instrument. The same dual role appears in the sky. A quasar absorption system uses alpha as a probe of cosmic stability. If the pattern of lines changed beyond known systematics, the constant would become evidence for a new field. In the absence of change, it restricts the theories that try to explain it dynamically. The same role appears in stone. Samarium nuclei in an ancient reactor had no purpose and recorded no message. Their surviving ratios now test whether an electromagnetic contribution shifted over geological time. A parameter entered a nuclear resonance, and the resonance became an archive. These are not disconnected curiosities added to make the number sound universal. They are consequences of the coupling entering distinct calculations. The causal spine remains one line. Define the dimensionless strength. Measure it independently. Watch theory carry it across phenomena. Change the probe scale and verify the running. Hold the scale fixed across time and search for variation. Ask a deeper theory to predict the boundary and the curve. At each step, a tempting shortcut failed. Units could not erase the ratio. Spectral recurrence could not derive the value. A probability slogan could not survive process dependence. A static formula could not survive running. Cosmic cooling could not substitute for scale dependence. Numerical coincidence could not substitute for independent prediction. Observer selection could not supply a distribution it had not justified. What survived is less ornate and more demanding. Alpha is the dimensionless electromagnetic coupling in the low energy limit. Its inverse is approximately 137.036. Independent precision roots measure it, with a notable unresolved tension between two atom recoil results. Quantum electrodynamics uses it to predict observables such as the electron magnetic anomaly. The effective coupling grows at higher energy in a way that experiments confirm. Tests using clocks, an ancient reactor, and quasar spectra have not established a change in the underlying low energy value across space or time. The standard model accepts the boundary value as an input. That is the complete answer currently available. It is not a failure to explain what the number does. It is an honest boundary on why the number is what it is. The boundary also tells us what the next answer must contain. It cannot merely print the right decimal. It must produce relationships. It must know about particle thresholds. It must survive the electron trap and the atom fountain. It must distinguish energy running from historical drift. It must explain why new forces or variations have remained hidden if its mechanism predicts them. The requirement protects us from being impressed too early. Humans are excellent at finding patterns after seeing a target. Physics earns trust by making a pattern arrive before the target is revealed. There is a final shift in perspective here. A fundamental constant can sound like the end of inquiry, a number fixed forever at the foundation. Alpha shows the opposite. Calling something fundamental can mark the place where the current layer stops. The word describes our model's present boundary, not a guarantee about nature's final depth. An earlier generation treated atoms as indivisible. A later theory opened them. The proton was once elementary in practical models. Quantum chromodynamics opened it. Space and time once supplied an unmoving stage. Relativity made the stage dynamical. Today's free parameters may remain fundamental, or they may become the surface of another structure. Alpha is unusually clean because it carries no unit fog. If a deeper layer exists, the demand cannot be shifted onto a ruler. The number waits in the same dimensionless form for any theory and any civilization capable of precision physics. That does not require the interstellar thought experiment in which strangers exchange a magic number. The evidence is already local. A rubidium atom absorbs light. An electron changes a quantum state. Hydrogen releases two colors that almost overlap. Electron and positron beams scatter at different energies. Samarium preserves a resonance. Iron and magnesium in a distant cloud remove narrow pieces of quasar light. Each event is ordinary within its own laboratory. Their relationships are the extraordinary part. The deepest success of the current theory is that it carries one measured coupling through all of them. The deepest omission is that it cannot tell us why that measured coupling begins where it does. Perhaps a unified interaction will eventually determine it. Perhaps the value will emerge from hidden geometry, a stabilized field, or a selection process embedded in a larger theory. Perhaps the final account will reveal that asking for one constant in isolation was the wrong question. Those possibilities remain inference and speculation, separated from the direct evidence that constrains them. For now, 137 is neither a code nor an oracle. It is a rounded signpost at the boundary between a theory that predicts almost everything we ask of electromagnetism and a theory that would explain why electromagnetism has this strength at all. The signpost is useful because it points in both directions. Behind it lies a century of calculations and measurements that agree with astonishing precision. Ahead lies a demand that no confirmed theory has met. The unresolved value does not make physics vague. It makes the missing piece exact. In the first scene, light pushed an atom, and the atom answered with a phase. By the end, that phase has become a question for the architecture of the standard model. The distance between those two statements is the real scale of alpha. It joins one photon kick to the search for a deeper law. An explanation will not be the formula that resembles the number most beautifully. It will be the theory that makes the number arrive, carries it through every measured scale, and predicts what the next experiment finds before the experiment tells it what to write.